Welcome to Basic Power System Analysis using PSSE. In this lecture, we are going to discuss how generator is modeled in PSSE dynamically. So before moving on, let us see what is the physical description of a typical synchronous machine. A typical synchronous machine consists of two sets of winding. One is the three-phase armature winding or the stator winding, which is static, and it has a three sets of winding which are 120 degree apart from each other. This is the reason why when this electromagnetic voltage is induced in the stator, we get three phase voltages which are 120 degree apart. The second set of winding is the field winding, which is available on the rotor, and this winding is supplied by the DC. The two basic configurations of rotor used are the salient or the projecting pole structure, which are mostly used in the hydro units, and these are usually used when we have a low speed prime movers. For instance, in the case of hydraulic systems, the prime mover usually operates at a RPM speed of 90 RPM, 100 RPM, 144 RPM, 200 RPM. So due to this low speed, we use this salient pole or projecting pole structure. Whereas the other type of rotor is the round rotor structure, which is mostly used by the thermal units or in the high speed units where you have 3600 RPM speed, 1800 RPM speed. So what are these salient poles? Salient poles have concentrated fields, usually also carry damper windings on their pole face. So how you can imagine these salient poles? Salient pole can be imagined like something of a hammer. Assume that a hammer is connected to the rotor. So this is salient pole is something similar to this, and we are going to see this in the next slide. The round rotor have solid steel with distributed winding. So it's a pretty cylindrical type of a rotor and having a uniform distribution all over with respect to the stator. Now, nearly sinusoidal spatial distribution of flux wave shape is obtained by distributing stator winding and field winding in the many slots and shaping pole faces salient pole. So how this is done? This is shown here. Now this is a salient pole rotor. As I said, this is the rotor and this is the projecting outward. So like a hammer, and the windings are available, these field windings are available on these salient poles. If you have a 4-pole machine, then you have the salient poles on each of the 4 poles. Whereas in case of round rotor, you will see that the rotor is uniformly, this field winding is uniformly distributed and it has a constant air gap or a uniform air gap between the rotor and the stator. So in this case, the flux density will be uniform, whereas in this case here the flux density will be different, whereas in this here the flux, so we are going to get a typically a ununiform type of a flux density when we talk about the salient pole rotor. Field winding. The field winding coils are inserted in axial slots in the rotor of a round rotor machine and around both sides of a main pole for a salient pole machine. So as we said before, in this case it is going to be in the round rotor, it is going to be here, whereas in salient pole it is going to be in these slots. So these are the axial slots, the windings are going to be here. The field winding coils provide the excitation flux. Direct current is supplied to the field winding coils through either slip or collector ring or from a rectifier output of a small alternator mounted on the same rotor shaft. So what happens? So now you have seen this physically, that we have this stator, and inside the stator is the rotor, and the supply to this rotor is provided, the supply provided to this rotor is DC supply. So how can we provide this DC supply? There are several methods to supply this DC supply. Either we provide it with the help of a DC shunt generator or with the help of some rectifier. So depending on this, but the thing is, the that we have to provide this DC current, and by controlling this DC current we will be able to control the flux of the generator, and by controlling this flux of the generator we can control the induced EMF into the stator winding. Now to calculate the impedances within this generator, now we have this physical generator which has this rotor, and then this has a stator, then it has uniform flux density, or in case of salient pole it has distributed density. So now how do we transform this actual or the physical parameter of the generator, synchronous generator, into the mathematical model? This is done with the help of Park's transformation. So what does this Park transformation say? Park transformations tell us that we can convert our physical generator attributes into an axis of two symmetry. This two symmetry axis is known as DQ axis or direct and quadrature axis. So what is the direct axis? Direct axis is the axis which passes through the center of the rotor and through the north pole. Directly through the center to the north pole. This is known as direct axis, and there is another axis which is exactly 90 degree to this D axis known as the quadrature axis. So for the purpose of describing synchronous machine characteristic, two axes are defined. These two axes are the direct axis and the quadrature axis, as I told you. So what we do, we convert all the physical attributes, this A axis, axis of phase A, axis of phase B, axis of phase C, the air gap and everything, and we transform them into DQ axis. So that is why you have seen that usually when we talk about transient reactance or subtransient reactance, we talk about X double D dash or X dash of D or XD. So this comes from the same thing. So a typical synchronous model for our dynamic stability studies is something like this. So we have this electrical model of the generator. This electrical model contains all the DQ axis. So this DQ axis value of, so the subtransient reactance in D axis, the subtransient reactance in Q axis, the transient reactance in both the axis, the synchronous reactance, the leakage reactances. So all the kind of reactances we have in the generator are modeled with the help of this generator rotor electrical. Then we have this excitation system. This is a separate model which interacts with the generator model, and what it is going to provide, it is going to provide the field voltages. So the rotor is going to be energized with the help of some field current. So this field current comes from the excitation system, and this provides us with the electrical attributes of the generator. Now on the other hand, we also have the mechanical attribute of the system. So what are this mechanical attribute? So we have this generator. This generator is connected to the turbine with the help of a shaft. So here we are going to have electrical torque. On the turbine side we are going to have mechanical torque, and from the output we are getting the electrical energy. So and the input is the mechanical energy. So number one thing we need to provide is the inertia of the shaft or inertia of the generator. So for the mechanical attribute we provide the inertia of the generator, which is coming from the which is directly, and the second thing we provide is the turbine governor characteristic. So how this T mechanical or the input energy is being provided to the mechanical part of the generator. So when mechanical torque will be provided to the generator, it is going to rotate at some speed, and this speed is going to directly affect my T electrical as well as my angle, because this is the same thing we discussed in the basics of transient stability. This is basically related to the swing equation. So with respect to swing equation, from here my T electrical and T mechanical will come, which will also interact with my inertia and the delta value. Now in PSSE, how we can see this? A typical structure or in PSSE is something like this. So when you will go to your drive where you have installed this PSSE, you are going to find the folder in program files, folder known as PTI. In this folder, when you will go, there will be another folder known as PSSE 32 or 33 or 34 or 35, whichever version you are using. When you go into this version, there is another folder with the name of docs. When you go into this docs, you will find a file known as model.pdf file, or there is going to be a folder with the name of model library, and inside this folder there is going to be a file known as model.pdf. When you will open this file, in this file you have all these models which are available in PSSE, which can be used to model different control features of different electrical equipment. So from there we are discussing one of the common type of model we use for this generator is the GENROU model. This is the round rotor model, and for the salient pole model we usually use GenCell. Now, irrespective of the model we are using, we need to understand what does this model tell us. So now this model tell us, number one, this is a typical. So if we assume this GENROU model or PSSE model to be a black box, so within this black box, what is going to happen? We are going to have some inputs and we are going to get some output from this model. So the input to this model are the P mechanical, which is going to come from the governor, field voltage, which are going to come from the exciter, and the terminal voltage, which will be available from the generator bus where this generator is connected. With these inputs, the GENROU model is going to perform some calculations on this, and on the output side it is going to provide me with the speed of the generator, the source current, the terminal voltage, and the angle of the generator. So these are the input and output of this model. So the cons also known as constants. So these are the constant different kind of parameters which will be required by this model, and the different type of parameters required by this model are the transient direct axis open circuit direct axis time constant. Similarly, subtransient direct axis open circuit time constant. Then in the Q axis same thing. Then the inertia, then the damping, then different kind of impedances, and in the end saturation. This saturation is also important because when a fault is going to come into the system and we may see that huge current is going to flow. Due to this flow of huge current, my generator can saturate, because this is a magnetic the magnetic interaction is there in the generator, and this magnetic interaction can cause the saturation of the generator. We have already seen these things. So this is going to be we have to provide this input, and from where we are going to get these values? We are going to get these values from the generator technical data sheet or from the nameplate. So whoever has provided with you with the generator, you can ask the manufacturer of the generator to provide these values, and these values are commonly available from the generator technical data sheet. Manufacturer data sheet provides these values. So you can just copy these values from there and add it here. Then the state variables which will be calculated during the simulation will be these. So these are also mentioned in my model library file. And the last thing is the GENROU diary file. This is exactly what we want to show you, that if you remember in our previous demonstrations, we simply use this diary file. So now how this diary file is created, we will show you how this diary file is created, but the syntax of the diary file is given here. If you see here, you have to provide this IBus, then you have to provide the name GENROU, then you have to provide the ID where this generator is connected. This is the bus number where generator is connected. This is the ID of the generator, and different constants values. So when you provide these values, you can simply add them in your notepad file and save this file as dir file, and that's it. Your diary file will be created.